Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at equation from the topic integral calculus. The equation reads: find the value of lambda such that the integral from -1 to 1 of e to the power cos inverse of x dx is equal to half all of that times lambda to the power pi plus 1. So without wasting much of your time, if you're just joining us in this channel, make sure you subscribe, you like the video, you comment in the comment section. Also, you have to pause the video and you try to get the value of lambda by yourself. Once you're done, you now join me and we solve together. Okay, so I believe you're already done finding your value of lambda. If you never found the value of lambda, then you have to watch till the end. Okay, so the first thing I'm going to do is I'm going to use a u substitution because the cos inverse here is kind of disturbing. So I'm going to let my u to be equal to cos inverse of x. Now, letting my u to be cos inverse of x, I can take cos on both sides. So cos u will be equal to x because cos of cos inverse of x is x in this interval -1 to 1. So my x is equal to cos u. Now I need to look for the x. Alright, so I'll differentiate both sides. I'll differentiate this side with respect to x and this side with respect to u. So the x is going to give me negative sine u du because if I differentiate cos u, I get negative sine u. So I'm going to have the x equal to negative sine u du. Now, after doing a u substitution and trying to get the x, I'm going to do the change of the integration limit. Here, I'm going to find the new limits of integration. The original limits of integration are x equal to -1 and x equal to 1, but the new limit will be u equal to something and u equal to something. So I begin when x is equal to -1, my u is cos inverse of -1, which is pi. So my lower bound is going to be pi. Now when x is equal to 1, my u is cos inverse of 1, which is 0. So my upper bound is going to be 0. This just means that my new integral is going to be defined in terms of u, and the integration limit will be from u equal to pi right up till u equal to 0, because when x was -1, u was pi, and when x was 1, u was 0, and -1 and 1 are the respective lower and upper bounds. Okay, so evaluating the integral is now what we are going to do. So my integral now will be equal to the integral from u equal to pi to u equal to 0 of e to the power u, because cos inverse of x was the u substitution, which is u, then the x is negative sine u du. Okay, now we need to use a property of definite integrals that says that the integral from pi to 0 of all of this, if I remove the negative sign here, I'll just need to switch the bounds. So I'll instead begin with 0 and I'll take 0 to pi. But with the negative sign there, we are going to integrate like this. But for us to remove this negative sign from here, we are going to switch the bounds. So I'm going to go ahead to remove that negative sign. So once I remove the negative sign, I switch my bounds. I now need to integrate from 0 to pi. I'm switching my bounds because normally 0 is less than pi. So I will want to integrate from a lower bound, which is less than, an upper bound. Okay, now there are two methods we can apply here to get the value of this integral. I'm going to use just one method, and it might be a method you are not familiar with. So I choose this method so that at least you should learn something new. A peculiar method we can always use to solve this integral is integration by parts, where we are going to do integration by parts 2 times, since we identify that this is a product of 2 functions in the same variable. So using integration by parts, the job is going to be done. But I'm going to use another method which you might not find familiar, which you might not be familiar with, but by the end of this video, I think you can apply that method whenever you arrive at such situations, and I think it's a little bit shorter than integration by parts. So that method is what we call using complex numbers. So we can identify that the sign of u can be written as an exponential function, knowing fully well that e to the power iu is equal to cos u plus I sine u. It therefore means that sine u is just the imaginary part of cos u plus I sine u. If I give you cos u plus I sine u, the imaginary part is sine u. So I'm going to replace sine u here with the imaginary part of e to the power iu. That is a definition. So this integral becomes the imaginary part of, I just replace sine u here with e to the power iu, taking into consideration that sine u is the imaginary part of that function e to the power iu. Now I use the exponential because attached to sine u I also have an exponential. So since they have the same base, I will add the powers. Adding the powers, I'm going to have u plus iu, and since u is common, we have u into 1 plus I. Now integrating an exponential function whose power is kind of linear, because I'm going to, in quotes, consider 1 plus I as kind of a constant. Okay, so the numerator, sorry, the power of my e is linear, which is u times 1 plus I. So to integrate this, well, how do we integrate an exponential function? We have to differentiate the power and then we multiply it by the same exponential function. But once we differentiate the power, we have to divide the exponential function by that derivative, which means that this is just going to give me, I'm going to differentiate u times 1 plus I. With respect to u, I'm just going to have 1 plus I, kind of the constant. Okay, then I have to put it in the denominator, then my numerator will be the same exponential function, which is e to the power u into 1 plus I, which is still the same as e to the u times e to the iu. Now we need to fit the bounds from 0 to pi. So when you fit pi, you're going to have e to the pi times e to the I pi minus the lower bound. When you fit 0, you have e to the 0 times e to the 0, which is e to the 0, and e to the power 0 is 1. Okay, so having in mind that your integral is equal to the imaginary part of this complex number here, okay, now we fully know well that e to the power I pi is equal to -1. There is a general principle, e to the power I pi plus 1 is equal to 0, okay, or we can say this e to the power I pi is cos pi plus I sin pi, but cos pi is -1 and sin pi is 0, so e to the power I pi is equal to -1. Okay, so e to the I pi being equal to -1, it means that this integral is the imaginary part of negative e to the pi, because this quantity here is -1, then -1. Now negative e to the pi minus 1 is a real number, so we can remove it out of this imaginary part because it is real. So removing it out, and factorizing the negative sign, then rationalizing 1 over 1 plus I. If we rationalize 1 over 1 plus I, we are going to have the conjugate of 1 plus I is 1 minus I, is going to come in the numerator. When I multiply the denominator with the conjugate of this denominator, I'm just going to have 2. That is 1 plus I times 1 minus I is just the sum of the squares of the real part and the imaginary part. So I'm going to have 1 squared plus -1 all squared, or 1 squared plus 1 squared, which is 2. So this is what we have. Now objective is to get the what is the imaginary part of 1 minus I over 2. It is -1 over 2, because 1 minus I over 2 is equivalent to 1 over 2 minus I over 2. So you see that the imaginary part of half plus -half I is -half. Okay, if you write it down, you'll get what I'm saying. So since the imaginary part of this complex number here is -half, we multiply that imaginary part with negative into e to the pi plus 1. We are just going to have the negative signs are going to cancel, and we are going to have half times e to the pi plus 1. This is equivalent to half into lambda to the pi plus 1 according to the equation. So from here we can deduce that lambda is equal to pi. So you can go ahead to use integration by parts, and you're also going to have the same result at the end of the day. So see you guys in the next video.